All right, in today's lesson, we're going to look at how to set up some Excel calculators that will work with various probability distributions, specifically the binomial, the Poisson, and the normal curve and the t-curve. Okay, so first we'll look at the discrete probability distributions, the binomial, and we'll just call it the P calculator or the Poisson calculator. But in any case, I've set up my template, right? So in yellow are the things that I will manually type in for each different question I need to answer. And then everything without a color will be automatically populated by Excel each time, depending on the situation. So for instance, right now I have 8 successes out of 24 trials with a probability of 42% of having a success. If I change this to 10, you will see that all of these changed automatically. You'll notice that the mean and the standard deviation didn't change because those are based solely on the number of trials and the probability of a success. If I were to change one of those, then you'll see that everything changed, including the mean and standard deviation. And that's just a standard format of what we'll call an Excel quote-unquote calculator, right? Something that can calculate things over and over for us. Okay, how do we do these? It's very simple. We're just using the binom.distribution function. Now, right now I'm showing you this in a Google Sheet, but it's identical in Excel. I'm just using the Google Sheet because it's easier to kind of change when I'm recording things. In any case, the function itself is equals binom.dist for binomial distribution, open parentheses. Then you have to give it 4 pieces of information. The first number it wants is the number of successes that you're working with, sometimes called X. Then comma, the second thing you need to give it is the sample size, the number of trials, N, comma, the next thing is the probability of a success, P, comma, and then the last thing you're going to give it is either true or false. False is only used for those cases when you want to find the probability of an exact number of successes. So in our first case, we want to know the probability of having exactly, in this case, 10 successes out of 20 trials with a probability of 0.42. So that's why I wrote exactly, so it can remind myself that, in English, when I'm looking at questions, it's probably going to ask for exactly this many. And then mathematically, that means we're looking for the probability of X. Remember, X is our number of successes is equal to some number. It's equal to this number, so we're looking for equal to 10. Okay, you can see that in my example, the way I've set up my binomial distribution function is instead of going in and manually typing in the different X, N, and P every single time, I'm using a cell reference. So instead of X, I've got I2, comma, instead of N, I've got I3, comma, instead of P, I've got I4, comma, and then false, because false is when we want to know exactly this many successes. Okay? Okay, so the first one we're going to do is the probability of being exactly a certain number of successes. So that's the binom.distribution function. And the first thing we have to tell it is the number of successes we're looking for. So in this case, 10. And then the number of trials we're doing total. So we're basically running the experiment 20 times, and we want to see half of them come up successes. And then the probability of a success, in this case, we set to be 42%. And in order to get an exact number of successes in the binomial distribution function, we just have to tell it the last thing is either true or false, and to get exactly 10, we say false. For all the others, we're going to do true. Okay, so instead of typing in 10, 20, and 0.42, we're going to do cell references of I2, I3, and I4. That way, for every new question, all we have to do is change the numbers in the yellow boxes, and then everything adjusts. Okay, that's the first one. Simple and easy. How about the next one? Now we need to be strictly less than this number. So we want the probability of our number of successes being anything that's less than 10. That means it could be 0 successes all the way up to including 9 successes, because you have to remember with binomial distributions, we're looking at discrete random variables, i.e. we're running an experiment where the answers can only be whole numbers. You couldn't get 9.1 or 9.5 or 9.2. If you have to be less than 10, you're going to be 9, right? Or 8, 7, 6, 5, 4, 3, 2, 1, or 0. Well, the binomial distribution function, as it's designed, right, as it was programmed within our spreadsheet, if you give it a number, so the first number you give it is x, and then comma the n, comma the p, and then you do comma true. When you do that, it gives you the probability of being less than or equal to x, whatever you put in for that first number. So if we did the binomial distribution of I2, comma I3, I4, and true, it would give us the probability of being less than or equal to 10, which is what we did down here. You'll see that it's just I2, I3, I4, because that's what we're looking for. We're looking for, at most, would be the English of it, but that means mathematically less than or equal to something. Well, in this case, we don't want less than or equal to, we want strictly less than. So we don't want to include 10, so we have to adjust it and make it I2 minus 1 as our x value. Right? So everything's still the same. We're still using the binomial distribution function. We're still giving it an x, an n, a p, and a true, but in this case we have to adjust the x to whatever the value in yellow is, minus 1. Now you might be thinking to yourself, well, why not just, use the normal, the same function that we used on line 8, but just change my answer in yellow to 9? Well, yeah, you could do that, but then that means every time you come across a question and it tells you it wants less than 10, you have to remember, oh, that's right. If I'm doing a less than 10, I have to actually put 9 into my binomial distribution function. And the whole point of making these quote-unquote calculators where everything is recalculated automatically for us when we change whatever is in the yellow squares is so that we don't have to remember those details. Because remembering you have to switch the number, that's not learning stats. That's learning how to use the binomial dot distribution function within Excel. We don't want to waste brain power on that. We want to understand what the binomial function does. We want to understand how we would apply it to a real life situation. Learning how the technology works, we just need to do that once to set up the stuff, and then we can forget about it. It's the same reason as we don't need to know how our calculators work. Okay, so we do I2 minus 1 because we want strictly less than. Now, the greater thans, both this one and this one, you'll notice use equals 1 minus the binomial distribution of some stuff, and this also uses equals 1 minus the binomial distribution of some stuff. Because, once again, the binomial distribution function as it is programmed within our spreadsheet, when you put a true for that last thing, right, instead of false, it gives you the probability of being 0 up through and including that value. So if we put 10, right, into the binomial distribution function, it gives us the probability of 0 successes up through and including 10. It adds all that together and gives us 1 probability. Well, if we want to be greater than the number, that's not what we get out of this function. We get the less than or equal to. But the nice thing is greater than a number is the complement of being less than or equal to something, right? If we want to be greater than 10, we want 11 through 20. Well, if we put 10 into the function, it's going to give us 0 through 10, and then 11 through 20 is just the other side of the argument. It's the complement. And we know that probabilities have to sum to 1. So if we calculated all 21 possibilities, right? So the case where we have no successes, then 1 success, 2 success, 3 success, all the way up to 20 success. That's 21 different ways the function could happen, right? 21 cases, I like to call them. If we calculated the probability of all of those and then added all those probabilities together, they have to add up to 1. That's what a probability distribution is. That's just the rules of how they work. So if we can calculate the probability of a clump of those and subtract that from 1, that will give us the probability of the other clump, right? Whatever's left over. So if we want everything greater than 10, all we have to do is calculate the probability of being 10 or smaller and subtract that from 1, which is what we do here. We do equals 1 minus the binomial distribution of I2, I3, I4, and true, because that uses 10, right, for our x value. The binomial distribution using 10 gives us the probability of being 0 through 10, and then when we do equals 1 minus that, it gives us the complement, which is the 11 and above, or i.e. the greater than 10 piece, which is what we wanted. And then the last one we have to deal with is, okay, what if we want to be greater than or equal to 10? Well, then we need 10 to be in the complement, right? We need that on the good stuff that's left behind. So when we subtract the lower end, when we do the 1 minus the binomial thing, we don't want to subtract away the 10 case. We only want to subtract away 0 through 9. So that's why we had to once again do this little adjustment where it's I2 minus 1. So now we're taking the binomial distribution of 9, and then we're subtracting that from 1, i.e. we're taking the function using 9 gives us the probability of being 0 through 9. And we add up all those probabilities. We subtract that sum from 1, and it gives us the leftover piece, which are the probabilities of 10 up through 20. The last two things is the mean and the standard deviation. Well, the mean of a binomial distribution is very easy to calculate. In fact, you really wouldn't even have to do this because it's so easy to do in your calculator. It's just simply n times p. But you might as well set it up so it always does it for you. So we just click on I3 asterisk I4, because that gives us n times p, and we get a mean. And then the standard deviation is also an easy formula to do by hand, because it is simply just the square root of n times p times q. So we use the equal SQRT, because that's the abbreviation for the square root function, and then inside the parentheses you put everything that's being square rooted. In this case, you click on I3 asterisk I4 asterisk, because remember asterisk stands for multiplication, and then in parentheses you have to put 1 minus I4 for q, because you have to remember that q is the complement of p. So if p is 42%, q would be 58%, right? And so if you do 1 minus I4, that calculates the complement. And you have to put that in parentheses for order of operations to make sure that first it calculates 1 minus I4 and it gets that q value. Then it takes that q value and it multiplies it by I4 and I3. And then you have to have that second parentheses to close off the initial parentheses, so all of that stuff is underneath the square root. Okay? And then that's your standard deviation. And that finishes off the binomial calculator for us. Now when we come over here and we do the Poisson calculator, the function is pretty similar, right? Instead of equals binom.dist, it's equals Poisson.dist. And then instead of giving it x and p and then true or false, you just give it x. It's kind of like the average of x. It's kind of like np put together, right? And then true or false. So you just have to remember, when to use each. The binomial is when you have a set number of experiments, right? A set number of trials, n, and then you're looking for a certain number of successes, x, within those number of trials. The Poisson calculator is you're still looking for a set number of successes, your x, but instead of having a set number of trials, n, you have a set interval of time. And then over that interval of time, you'll have an average number of successes. So that's why you have mean number of successes for that second number in yellow. The only thing you have to remember when doing these questions is you have to make sure that the average, right, the mean number of successes that you have in N3, that cell up there, is the same time period as the time period you're investigating. So you're looking for, in this case, 62 number of successes over some time period that has an average of 65. So if they told you, for instance, let's just make the numbers easier, so we can do the math in our head. Let's say it's the average is 60, and we're looking for 25. We're looking for 35. There we go. Actually gets us some numbers, right? Let's do even 40, just so everything's not a bunch of zeros. Okay. So an average of 60 over some time period. It could be one day. It could be 1 hour. It could be 3 days. It could be 7 minutes. It could be 12 hours. Whatever that interval is, it has to be the same interval for the number of successes we're looking for. So if we're looking for 40 successes over 7 days, then we need to know what the average normally is over 7 days. If we were looking for 40 successes in an hour, then we need to know what the average is over an hour. So if they told us something like, there are 120 calls that come into your call center every hour, and then what's the probability that you get 40 calls in the first 30 minutes? Well, 120 over an hour means on average you get 60 in 30 minutes. And so now if we're looking for 40 in 30 minutes, we would have to adjust that average of 120 over an hour down to 60 over 30 minutes. You get where I'm going with this? So that's how the Poisson function works. So we just have to make sure we make those adjustments when we're doing it here in our spreadsheet. And then calculating all of these is pretty much the exact same thing as calculating all of these. If we're going to do equals, it's just n2, n3, and false because it's strictly equal. Over here, right, when we did less than, we had to do that whole -1 thing for our value. So it was I2 minus 1. Over here, it becomes n2 minus 1. For this one, we had the 1 minus. For this one, we have 1 minus. But instead of doing 1 minus the whole function, we can just do 1 minus n7, because you may have noticed that over here, 69% and 30%, these add to 100. Now I know 69 plus 30 is 99, but if you do 69.36, right, if you add those two numbers, they're always exactly 1, just like these two numbers are always exactly 1. They're complements of each other. So instead of typing in, this whole function 1 minus the blah, 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 blah each time, we can just go, you know what, it's just going to be 1 minus the thing that I'm going to get down here, because this one's really easy. The less than or equal to, remember, we didn't have to do any adjustment at all. It was just use the value that we have for our number of successes. And then this one is always just going to be 1 minus that. And then same thing for this greater than, right? Greater than or equal to was 1 minus with the adjustment. So instead of having to do that, we can just do it's 1 minus this one here in cell 5, where we've already done the adjustment. And then we've quickly finished off the Poisson calculator. And it's just that simple. Okay? You can use the same kind of idea for the norm dot distribution and the t dot distribution functions. You just have to know what you need to type into your functions. So when you're doing the norm dot distribution function, the first number it wants, Q5, is your x, your number of successes you're looking for. The second number it wants, Q2, is the average, the average of your distribution, because now we're dealing with a continuous random variable, so we don't have a number of trials, we have an average number of things. So that's my Q2. Then the next thing it wants is the sample size. Now I've got my sample size set up as Q3 divided by the square root. Sorry, it's not sample size. It's your standard deviation. I'm sorry. And your standard deviation is always the population standard deviation, which in this case is Q3. But then we have to divide that by the square root of our sample size. So sometimes they'll ask you, what's the probability that if you, do the experiment once, i.e. you have a sample size of 1, that your the probability is less than this type of thing, or what's the probability that it's greater than this number of things. Well, in that case, your standard deviation is still the same as the population standard deviation because you're only sampling one thing. But once you study the central limit theorem, you realize that if you're now going to take a sample of a certain size, the standard deviation of that new sampling distribution is always the population standard deviation divided by the square root of your sample size. So that's why we defined the third piece where the function wants to know what the sampling distribution standard deviation is. It's going to be Q3 divided by the square root of Q4, because Q3 is the population standard deviation and then Q4 is our sample size. And then the last thing we give it is just like the other ones, the true or the false. The true gives us the probability of being less than or equal to our first value, our x, in this case Q5. A false would give us the probability of being specifically equal to Q5, which we know in theory is really 0. But what this function does, if we put a false in there, is it gives us a close approximation by giving us a little tiny interval around whatever our Q5 value is. Okay, you'll notice that I just have less than and P is less than our test value X. Remember that it's the exact same thing if it's less than or equal to, right? It doesn't change our probabilities whether it's a less than or equal to. Same thing with greater than or greater than or equal to. So we don't have to have all of these extra cases over here like we do in the binomial. We just have, it's either smaller or it's bigger. So smaller, that's the way the function is designed. So we just do the function normal. And then bigger is the complement. So it's 1 minus that. So here's my 1 minus. And again, I can cheat the system, so to speak, and rather than doing 1 minus and then the whole norm dot distribution, blah, 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 again, I can simply just do 1 minus Q6 because these two numbers will always be perfect complements, right? These two numbers will always add up to 1. Okay, so that's less than and greater than, really, really super easy. You would do the exact same thing over here, except you're using the t distribution function, and then you have to give it a degrees of freedom stuff, and we can talk about that in another video, or I'll let you guys figure it out. Actually, do some stuff on your own, and then the same thing as 1 minus t6. Okay, the idea of being in between two things, right? So what's the probability that we get in between two values? So we have to tell ourselves what the second value is. So in this case, I've set it up where down here would be the larger of the two. In this scenario, we're looking for the probability of being between 49.4 and 155, where the average is 49.9, the standard deviation is 3.74, and we're going to take a sample size of 12. So to do the probability in between, we have to use the norm.distribution function for the larger number, right? So I remind myself here in this little box that x2 is the larger of the two x's, so that's why I put 155 here. And so that's why it is using Q12 inside the function, right? See Q12, it's using 155. And then everything is the same. Q2 is the mean, right? Q3 divided by the square root of Q4, that's my standard deviation because I have to divide by the square root of the sample size. And then I do true, and I close the parentheses, and that first bit just gives me the probability of being less than 155, but I want to be in between the two, so I have to subtract away being less than the 49.4, so that's why I have this minus Q6. I'm just taking away the probability of being less than the lower one, and that gives me the probability in between. Then the last piece is what if they ask the question where instead of, hey, here's a value for x, what's the probability of being less than x? Or here's a value for x, what's the probability of being greater than x? Or here are two different values for x, what's the probability of being in between those x's, right? That's what the norm.distribution function does. What if they ask the question in reverse? Instead of giving you the x and asking for a probability, they give you the probability and they ask you to solve backwards for the x. So something like, hey, what value of x would you need in order to be in the 98th percentile, right? To have 98% below you. Then that requires, and in this case, I put 97.5. I should probably show some more decimals so I know what number is actually sitting there. If I wanted 98, I'd have to type in 98. But in any case, to do that, we use the norm.inverse function, or in Google Sheets, it's just norm in, but I'm pretty sure you could do norm.in here as well. But the old standard, well, let me check. I'm pretty sure. Let me put a stupid period in there and see. Yep, still works. Yeah. So the norm.in and the old style of these is they didn't put the dot in between things. So you could use either one, but .inv for inverse is the new kind of naming a scheme that they use for all of their functions in the spreadsheets. And then you just have to know what you give it. And down here it tells you the first number it wants is x. And in this case, x is the probability. They really should have called it something else because x makes you think, oh, it's the x up here. No, because the x is actually what this function is going to give us. It's actually going to give us what the x is. This should have been called probability. So it's looking for the probability, comma, then the mean, comma, standard deviation. So you can see that's why I've got Q18, because that's the cell here where I'm going to put the probability as a decimal, by the way. So I just formatted this cell to display the number as a percentage. And the nice thing about your spreadsheet is now if I want 95%, I actually type in 95. I don't have to remember to type it in as 0.95 as a decimal, because I have it formatted as a percentage. And then the spreadsheet is smart enough to then store that number or use the number of 0.95, the mathematical equivalent of it in the function. And then comma, I click on, Q2 for the mean, and then that same old thing of Q3 divided by the square root for the standard deviation. Okay, so as you can see, if I want this to be 95%, I type in 95, not 0.95, but it's still doing the math correctly for me, and it's still giving me, okay, a value of 51 would have 95% of the stuff below it. Okay, that's it. I'm not going to spend time going over the T-curve yet. I'll do that in another video because I don't want this one to get too long. I hope that helps.